Hi, this is John Whitaker for the Mathematical Analysis 2 class. This is lecture 16, and we're going to start today with the theorem. It's called the change of variables theorem for integration. And here's what it states. It says, suppose phi is a strictly increasing continuous function on, or I should say that maps the interval capital A to capital B onto the closed interval from little a to little b. Suppose alpha is monotonically increasing on A to B, and F is a Riemann-Stieltjes integral function with respect to alpha on A to B. Define this big B and G on capital A to B by big B of y is equal to alpha of phi of y, and and g of y is equal to f of phi of y. Then g is Riemann-Stieltjes integral with respect to b on big A to B, and the integral from big A to big B of g dB is the same thing as the integral from little a to little b of f d alpha. And we call this theorem the change of variable, but really this is a generalization of U substitution integration technique. Okay, here's the proof. Okay, if we're trying to show that G is Riemann-Stieltjes integral with respect to B, let us first consider or let Q be, well, let's let it be equal to y sub 0, y sub 1, all the way up to y sub n. And that's going to be a partition of the interval big A up to big B. Then phi of yi, this set as I run from 1 to n, if you will, forms a partition the interval from little a to little b. And I'd like to explain this just a little bit. This is true because, okay, first of all, phi of A has to be equal to, phi of big A has to be equal to little a, as phi is onto A to B. So that means that something from big A to big B has to be sent to this little a, and phi is increasing. So if phi of big A is an A, then there's nothing in big A to big B such that phi of that number will be equal to little a because it's going to be bigger than A. Okay? Also, phi of y sub n, which really equals to phi of b, that's going to be equal to little b. Remember this phi of a, that's really the same thing as phi of y sub 1. Write that down, same thing. This last statement is true as phi is onto A to B and increasing. Okay. The ordering of the points is also held true in these partitions by phi because it's increasing. Now, on the other hand, if we let script p equal to x0, x1, up to xn be a partition of A to B, then phi inverse acting on the xi's, as I run from 1n, is a partition of big A up to big B, that interval, as phi inverse will be onto big A to B, and phi inverse will also be increasing. I'm not showing the details of this phi inverse being increasing, but it is. Now, if we let x be an element of A to B, then there exists a unique y element of big A to B such that phi of y is going to be equal to x. That's what we have. Okay, since g of y equals to f of phi of y, this was in the parent statement in the definition of g of y, that's going to be equal to f of x. That gives us the fact that the values taken on by f on the subintervals given by a partition from x sub I minus 1 up to x sub I are exactly the same. Taken on by G, the function G, on the corresponding subintervals in the different partition, that's y sub I minus 1 up to y sub I. Also, since the B of y is defined to be alpha acting on P of y, then B of yi is equal to alpha of x sub I. Thus, we'll get that the upper sum with some partition of big A to big B with G with respect to B, that's going to be equal to the upper sum of any partition of little a to b with F alpha. And similarly, we have the same statement for lower sums. All right. Now, if we let epsilon be greater than 0 be given, since we're assuming that f is Riemann-Stieltjes integral with respect to alpha on a to b, then there exists a partition p sub 1 such that the upper Riemann-Stieltjes sum minus the lower Riemann-Stieltjes sum with respect to this partition p sub 1, that's less than epsilon. So what we have then, that means there exists a q sub 1. It's a partition of big A to B such that the upper Riemann-Stieltjes sum with Q, G, and beta minus the lower sum with Q, G, and beta will be less than epsilon. That tells us, of course, by our biggest theorem in terms of determining whether a function is Riemann-Stieltjes integral, that G is Riemann-Stieltjes integral with respect to beta. Now note, then we're from A to B of G dB. That's going to be equal to the nth over all partitions Q of the upper sums, but that's going to be equal to the nth over all partitions P. Remember, this Q is partitions of big A to B. This P is partitions for little a to B. P F with alpha And that's just equal to the interval from A to B of f d alpha. And so that proves the result. Well, that's our theorem, which gives us the ability to use substitution as an integration. Here's our next theorem. Our next theorem is untitled, a fundamental theorem of calculus. Part 1. And here's what it says. It says, let f the Riemann interval on A to B. And then for A being less than or equal to X being less than or equal to B. Put big F of X equal to the interval from A to X of F of T dt. Then big F of X is continuous on A to B. Furthermore, if F is continuous, at a point x sub naught in A to B, then big F is differentiable at x naught, and big F's derivative equals to little f at x naught. And this kind of gives us an indication that differentiation and integration are opposite processes. Here's the proof. Since little f is assumed to be Riemann interval on A to B, then f is bounded on A to B. So let's suppose, just for symbolic benefit, that f of t inside absolute values is less than or equal to m for all t element of A to B. Now, if we have A is less than or equal to x, is less than or equal to y, is less than or equal to b, then when we look at big F of y minus big F of x inside absolute values, that's equal to, okay, this is equal to this interval. So this interval from A to y, little f of t, minus the integral from a to x of little f of t. And that's going to be equal to the integral of, it's going to be x to y of f of t dt, since y is bigger. And that's going to be less than or equal to the integral of the absolute value of f of t, x to y, dt. And that is less than or equal to m times y minus x. Great. Okay, now if we let epsilon be greater than 0 be given, then whenever y minus x inside absolute values is less than epsilon over m, then the absolute value of f sub y minus big F of x, this will be less than epsilon. There's a little bit of work here because, I'm assuming that x is less than y here, and here I'm not. But the absolute value, you can run down the details there to get this result. Put yourselves in a similar situation to get this. Okay, let me just write it here. So we were given an epsilon greater than 0, and what we showed was, provided that the y's are close to x, then within this delta units, then we can make the output values be close to f of x within epsilon units. And that says that f is continuous at x, okay? And x was just an arbitrary point, and a to b. And so this means f is continuous on a to b. That's part of what we wanted to get. Okay. Okay, now to do more, to get to more of what the theorem says, suppose f is continuous at x naught. What we're trying to do is we want to show that f prime of x naught equals to little f of x naught. That's what we want to show. And what that means, that is, we want to show that the limit as t goes to x of big F of t minus big F of x naught, this should t goes to x naught here, over t minus x naught, that that's equal to f of x naught. So this is a limit that we're trying to show. So the way we show this limit is what we hold. Is we let epsilon be greater than 0 be given. We need a delta greater than 0 such that for all t element of AB with 0 less than t minus x naught less than delta, then, all right, right here, this absolute value of f of t minus f of x naught all over t minus x naught minus little f of x naught will be less than epsilon. Okay. First of all, let's recall that since f is continuous at x naught, okay, since f is continuous at x naught, we've been given epsilon, we've been given epsilon. There does exist a delta greater than 0, such that for every t element of A to B with t minus x naught being less than delta, then f of little f of t minus little f of x naught will be less than epsilon. Okay, beforehand, I did some work on this side of the board just a few minutes ago, in which I said, okay, look, with the absolute values involved, we get the result that we want. I didn't break it down into all cases to verify it. I said, well, it can be done. But this time I'm going to be a little bit more careful. Here, for case 1, in the thing we're trying to prove, let us suppose that t is greater than x naught. Okay. Then, what we're trying to look at is this absolute value, big F of t minus big F of x naught all over t minus x naught minus f of x naught. We wanted to look at this. We hope to show it's less than epsilon. Okay, here's what I got. Now t is bigger than x naught. Here's what we get. This is equal to, this will be the integral from a to t of little f of, let's say, u du minus the integral from a to x naught f of u du all over t minus x naught and then minus f of x naught. Okay, and then this is equal to the absolute value. Okay, t is bigger, so what I'm going to get is the integral. The difference here is going to be the integral from x naught up to t of f of u over t minus x naught minus, and here I'm going to get a common denominator. I'm going to say, well, it's f of x naught times t minus x naught over t minus x naught. Okay, well, this is 1 over t minus x naught. Essentially, what we're doing here is we're writing this down as one fraction, and, okay, writing this down as one fraction, this minus this, all over the bottom. The absolute value of a fraction is absolute value at the top of the absolute value at the bottom. I'm pulling out the absolute value at the bottom. For t is bigger than x naught, so it's just 1 over t minus x naught. Minus x naught t f u du minus this f of x naught, which is just a constant, times t minus x naught. All right, here I'll say this is 1 over t minus x naught. I'll rewrite this as the absolute value of the integral from x naught up to t, and this I'll say is f of u minus f of x naught du. Okay, let me stop for a second. Look, the integral of these things is the integral of this guy minus the integral of this guy. The integral of that guy is right here. What's the integral of f of x naught? Well, that's just a constant. So the integral of f of x naught with respect to u is f of x naught times this t minus x naught, which we've seen as the fact. Did that earlier. It's du here. Okay, so that's one rule. Okay. Now, we bring in the absolute values and say this is less than or equal to 1 over t minus x naught, integral from x naught to t of absolute value of f of u minus f of x naught du. Okay. Now, if the absolute value of t minus x naught is less than delta, then the original problem we're looking at, the absolute value of f of t minus alpha of x naught, all over t minus x naught, minus little f of x naught, which is going to be less than or equal to what we just wrote, 1 over t minus x naught, integral from x naught to t of the absolute value of f of u minus f of x naught du is going to be less than or equal to 1 over the t minus x naught. And then I can replace that absolute value quantity because of the continuity of little f at x naught by that guy being less than epsilon. So here, this is going to be epsilon times t minus, well, that was terrible, t minus x naught. Okay? And these t minus x naughts cancel. And so we just say that's equal to epsilon. Okay. And I put less than or equal to here, but really, I'm replacing this with epsilon. So it's really we have less than. Yes. So here, this should have been just strictly less than. So in this case, we have that absolute value of f of t minus f of x naught all over t minus x naught minus f of x naught is going to be less than epsilon. Okay, look at case 2. That's where t is less than x naught. Then this absolute value of f of t minus f of x naught all over t minus x naught minus little f of x naught. That's going to be equal to the absolute value, this is an integral from a to t as we had before, of f of u du minus the integral from a to x naught of f of u du all over this t minus x naught minus the f of x naught, little f of x naught. And here this is going to be equal to the absolute value. Well, this difference this time is going to be a minus t to x naught, as I've written it, f of u du all over t minus x naught. And here I'll say minus little f of x naught. Let's apply that minus to what's below. And so this becomes the absolute value of the integral from t x to x naught of f of u du over x naught minus t, and getting the common denominator, of course, here, what's right, it's little f of x naught times x naught minus t. Which is equal to, over x naught minus t, which is equal to 1 over x naught minus t x naught minus t times the absolute value from the interval from t to x naught of f of u, and again this is minus f of x naught du, which we will say is less than or equal to 1 over x naught minus t times the interval, the interval from t to x naught of the absolute value of f of u minus f of x naught du. Okay. So if, again, we have that t minus x naught is less than delta, then this absolute value of f of t minus f of x naught, that's the big ones, all over t minus x naught minus little f of x naught inside absolute value. Well, we got it being less than this quantity. So let me write that down. It's less than or equal to 1 over, this is x naught here, minus t, interval from t to x naught, that's the value of f of u minus f of x naught du, I want to write that down, which is going to be less than, okay, this part right here is less than epsilon, so this is less than 1 over x naught minus t. This is going to be epsilon times x naught minus t, and I was right here in the corner, which is going to be equal to epsilon. So in all cases, f of t minus f of x naught all over t minus x naught inside absolute values minus f of x naught, little f of x naught, is going to be less than the given epsilon whenever 0 is less than t minus x naught is less than delta. So that says that the derivative of big F of x naught is equal to f, little f evaluated x naught. That's that proof. Okay, the next theorem I want to get up is known by most people as fundamental theorem of calculus. I'm going to write down as the fundamental theorem of calculus. Part 2. And here's what it says. It says if f is a Riemann integral on a to b, and if there is a differentiable function big F on a to b such that big F prime equals to little f, that's a little f, then the interval from a A to B of little f of x dx is equal to big F evaluated at B minus big F evaluated at A. Let's look at proof. We're on the left, epsilon is greater than 0. Give it. Okay, we choose a partition, script P, which we'll write down x of 0, x of 1, all the way up to x again, of A to B, so that, because F being a Riemann interval, the upper sum of the partition minus the lower sum of the partition is less than epsilon. Okay. Well, the mean value here acting on big F, gives points T sub i's. They're in the subinterval from x sub I minus 1 up to x sub I of our partition. So I'm thinking about big F. Such that big F prime of T sub I equals to f of x sub I minus f of x sub I minus 1 all over this x sub I minus x sub I minus 1. Okay. So this big F is nothing more than little f evaluated T sub I. So little f, that's a little f this time, evaluated at T sub I times, I'll write down x sub I minus x sub I minus 1 is equal to f of x sub I minus big F of x sub I minus 1. Sorry about that. So that says that f of T sub I, this other quantity there is symbolized by delta x sub I, and that's equal to f of x sub I minus f of x sub I minus 1. So, the sum as I runs from 1 to n of the f of T sub I times delta x sub I will be equal to the sum as I runs from 1 to n. This will be f of x sub I minus big F of x sub I minus 1. We've looked at these sums several times before. What happens is that there's a lot of cancellation if you write out the expansion of this sum, and you just end up getting f of b minus f of a. So, So by a previous theorem, really it was it was a theorem that had to do with that main theorem of proving something with Riemann-Stieltjes integral using that epsilon. We had some three-pronged theorem that would result of that. We have that the sum of the f sub t sub i's as I run from 1 to n times the delta x sub I minus the integral from a to b of f of x dx. Inside f sub a will be less than epsilon. Thus, we have the f of b minus f of a minus this integral from a to b of little f of x dx inside f sub a is less than epsilon. Now, since epsilon is arbitrary, what we're saying here is there's no distance between these guys. And so that means then this integral equals f of b minus f of a. Okay, that ends that proof. Last theorem I would like to get up for this lecture is the integration by parts theorem. And here's what it says. It says, suppose f and g are differentiable on a to b, f prime equals to little f, and little f is Riemann integral, and big G prime equals to little g, which is Riemann integral. Then the integral of big F of x from a to b times little g of x dx is equal to f of b times big F of b times big G of b minus big F of a times g, big G of a, minus the integral from a to b of little f of x times big G of x dx. Okay, here's the proof. We let h of x be equal to big F of x times big G of x. Okay? Okay. Since big F and G are differentiable, then they are continuous, and thus h is Riemann integral. How we did that? That's because we know the product of Riemann integral functions are Riemann integral. Okay. Also, h prime of x by the product rule, that's going to be equal to f of x times g prime of x plus f prime of x times big G of x, and replacing the primes by what they're equal to. This f of x times little g plus little f times big G. That's how we write it. Now, big F, little g, big G, little f are all Riemann integral. So H prime is Riemann integral. Thus, by the fundamental theorem of calculus, part 2, we have the integral from a to b of big H prime of x equals to, by the way, this is equal to h of b minus h of a. Is equal to the integral from a to b, so let's replace h prime with what it's equal to, of f times little g plus big G times little f, which of course we can rewrite as two integrals, a to b of big F G plus the integral from a to b of big G F, little f. So, the integral from a to b of big F times little g is going to be equal to h of b minus h of a minus the integral from a to b of big G times little f. And that's just equal to, well, h was the product, so this is f of b times g of b minus, again, using the fact that h is a product of big F and big G. This is f of a times big G of a minus the integral from a to b of big G of f. And that's what's our conclusion of our theorem. Okay, ladies and gentlemen, that ends the integration by parts theorem, and that ends this lecture. Thank you very much.